Okay, another question I asked some of my students, as sort of a puzzler, was this idea that, here's the Earth. It has a mass of big M, and when you stand outside the Earth, or you stand on the Earth's surface, the gravitational pull you feel is little g. So, little g is pulling you down like that. Okay, little g is the magnitude of the Earth's gravitational pull on the outside. And Earth has a certain density. And I'm going to say the Earth's density is about 10 to the third kilograms per cubic meter. That's very approximate. It's actually 4 or 5 times that much. But I'm just going for an order of magnitude thing here. Because what we're going to say, and this is going to be rho for the Earth, and I'll call that g for the Earth. And so what we're going to say is there's this freak physics accident. I think I said, it involves an aardvark and some other stuff. So maybe we can call this the aardvark problem. And it compresses the Earth. The entire mass of the Earth stays the same, but it compresses the Earth down into a ball of neutronium, which is the material. It's degenerate matter. It's where basically everything is a bunch of neutrons that are all smashed tightly together. And the density of neutronium is about 10 to the 18th kilograms per cubic meter. So the Earth, it's the same mass of Earth, but everything's been turned into neutronium, which means it's collapsed down to this tiny little ball because it's much denser. And you are the last person alive, although only very briefly, as we'll see. And that's supposed to be an error there. And so we want to know what is the surface gravity as you are standing on this neutronium ball. So the way to approach this, really this is just a question of scale, and you can do everything with ratios here. You actually don't need any information more than what we've done here. You don't need the mass of the Earth. You don't need to calculate explicitly the radius. You can just find rho n would be the density of the neutronium. So let's look first of all at how the radius changes if you have an object of the same mass but the density changes. So start with the definition of density. Density is mass divided by volume, right? Okay. Now, volume of and these are spheres, right? So the sphere has a radius. So, the Earth, normal Earth has some radius, we'll call it RE, and neutronium Earth has some radius Rn, which I won't draw because it's tiny, but you can see, well, there it is. Okay. If you want to zoom in and see that, you can see all the pixels that make it up. So, what's the volume of the Earth? Well, now you might remember what the formula for volume of a sphere is, but I don't, or really I'm going to pretend I don't. All I remember is that the volume of a sphere is somehow proportional to the cube of its radius. So I'm going to say the volume of a sphere is equal to capital B times the cube of its radius. I don't remember what B is. I actually do, but I'm not going to pretend I don't. Okay, so V. So I'm just going to say the density of the sphere is equal to the mass divided by b r cubed. Okay, so let's make a little ratio here and say density of Earth divided by density of neutronium is going to be equal to, and then we just plug these fractions in. So this is going to be m over b radius of the Earth cubed over m over b radius of neutronium Earth cubed. Okay, I'm calling it neutronium Earth. Okay, so this now the thing is here. Now you've got your all this in place. M cancels, and b cancels too. So if you remembered that b is actually 4/3 pi, because that's our formula for the volume of a sphere, then bully for you. But it cancels out anyway, so it doesn't matter. So what you get then is, and then remember, this is the Rn cubed here is in the denominator of the denominator, so it actually goes up into the numerator. And this is in the denominator of the numerator, so it goes down into the denominator, so Re cubed. And what this means then, if we take it down one more step, is that Rn over Re equals the cube root of Earth's density over neutronium density. And so if we plug in some numbers here, this is 10 to the third. The cube root of 10 to the third divided by 10 to the 18th. So it's the cube root of 10 to the third divided by 18th. So it's actually 10 to the minus 15th, which means it's 10 to the minus 5th. So the radius of Neutronium Earth is 1/100,000th the radius of normal Earth. So if you happen to remember that the radius of the Earth is RE is like approximately 6 times 10 to the third kilometers, maybe 6 times 10 to the 6 meters, then you multiply that by 10 to the minus 5. So radius of Neutronium Earth is about it's tiny. It's about 60 meters, right? Yeah. So the Earth has been compressed down to this neutronium ball with a radius of 60 meters, which means the whole diameter is 120 meters, so it's barely bigger than a football field. That's how dense neutronium is. Anyway, so now finding the surface gravity. Well, say you have mass m, and so your weight on the surface of Earth is m times Earth's gravity, right? This g sub e is your acceleration on the surface of the Earth from gravity, so that's just that. And that's your force from the Earth's gravity. So that's going to give g times Earth's mass times your mass divided by a radius of Earth squared, right? Well, and then you do the same thing for the neutronium sphere, and so mgn equals big G times mass of the Earth times your mass divided by a radius of neutronium sphere squared. Well, now what we can actually do is we can actually take these equations and just divide them by each other. So this, let's see, this equaled this equaled this, but really we could just make big fractions and say the ratio of the two is equal, right? So now, what cancels? Well, m cancels here, big M cancels, that's mass of the Earth, stays the same, G cancels. So what you get now is that, and actually I'm going to flip this over, and again, this is denominator of the numerator, so this goes down to the denominator. This is denominator of the denominator, so it becomes the numerator. So GE over GN equals RN squared over RE squared. And the way I'd really prefer to express this, actually, so I'm going to do it like this, is GN equals, let's see, so this is coming up here. So that must mean this goes over there, right? RE over RN. And instead of squaring, top and bottom, I'm just going to square the whole thing times G for the Earth. I'm just going to call that G. That's regular old familiar everyday G. G from the happy days before the accident that destroyed the world. So now that we're in this nightmare world where we've turned the Earth into this neutronium sphere, the gravity on the surface is going to equal the ratio, by which the radius change squared times regular G. And so this is 10 to the negative 5 was Rn over Re. Well, this is the inverse of that. So this is 10 to the 5. So I'm just going to write this. I'm going to write this in red letters because tomato paste is red, and tomato paste is what you're going to be after you stand on neutronium Earth. So Gn is Re over Rn is 10 to the 5th. It's the inverse of this. So 10 to the 5th, and then but we square that, so it's actually 10 to the 10th times regular G. So there you go. You're standing on the Earth and feeling normal G, and then horrible accident turns it into neutronium, and you feel let's see, what is that? 10 to the 10th. So that is 10 billion G's of gravity smashing you into, as I said, tomato paste, which then gets smeared over the whole surface of this neutronium sphere and probably turned into neutronium itself. But anyway, that's another story. So that is the sad story of neutronium Earth.